Good morning and welcome. This morning we're going to be talking about antenna basics. So in general, radio antennas come in a large variety of forms, but we're only going to be talking about the ones that are really relevant to radio astronomy because there's just too many to cover otherwise. So we're going to start with the simplest example and then we're going to move up through some examples until we get to the most commonly used radio antenna, the parabolic reflector. So the first thing to note is this concept of reciprocity. So reciprocity means that an antenna has the same properties whether it's receiving or transmitting radio waves. So for measuring how an antenna performs, instead of trying to do that by having the antenna receive, you can have the antenna transmit instead and then look at the power it's radiating around it to see how sensitive it would be. But we'll get into that later. So let's start with the components of a radio antenna. So you'll have some support structure which you can use to move the telescope, the primary reflector, a subreflector which is supported above the main reflector, and a feed housing where you have your feed antenna which feeds the signals into your receiver. So in general, what's happening is radio waves are coming from space. They're reflecting off the main dish, hitting the subreflector, going into the feed horn, being received by a receiver somewhere, either on the telescope or in a building, and then you digitize them and look at them on a computer. So let's start with the most basic antenna we have, which is the dipole antenna. So this is really just a piece of wire. Pretty much, sort of two pieces of wire. Now you need to tune your dipole antenna to the wavelength of light you want to look at. So for a standard dipole, you want the length to be about the wavelength of light you're looking at. But for radio wavelengths, that can be a bit long. So you can also have a half-wave dipole, and in that case, the length of your dipole antenna will be about half the wavelength of the light you're looking at. So again, these are just two pieces of metal wire with a resistor between them. Now, the beam pattern, the radiation pattern of this antenna is sort of a torus or donut shape, which I'll show you in a couple of slides. It'll be easier to see then. So this, if you were to take a two-dimensional slice of that torus pattern, you'd get a double-lobed pattern. So pretty much that pattern would be sort of a figure 8 double lobe that went like this. But again, I'll show that in a few slides. It'll be more clear. So what's happening is the way that this antenna is detecting a radio wave is that an electromagnetic wave is coming by it. And the electric field is causing electrons in these metal wires. This is why these wires are metal. The electric field is causing electrons to move in the wires. And that creates a current. And as long as we have some resistance, we can measure the current. Because, if you don't know, voltage equals current times resistance. So we need if we have a current, we need a resistance to be able to measure a voltage across that resistor. So this resistor is in general our receiver. And again, I said, for longer radio wavelengths, your dipole can get quite long if you're using a standard dipole. So to keep it short, we generally use half-wave dipoles. Now, one thing to note is a single antenna is only sensitive to one polarization. So if we go to the next slide, we can see here we have an electromagnetic wave coming in, so it's moving from the lower left here up to the upper right. We're ignoring the magnetic field, the oscillating magnetic field in this electromagnetic wave, because we don't care about it. We care what we're measuring is the electric field here. So you can see, obviously, at some points, the electric field, is pointed to the left, and then sometime later as the wave travels, the electric field's pointed to the right. And you can see, say, when the electric field's pointing to the left, you can see electrons moving in this leftmost wire towards the end of it. And then when the other half of the wave comes by, the electrons start to flow in the other direction and move towards the right side of the dipole. So you can see the dipole becoming alternately charged positive and negative on each side. And you can see sort of the total voltage, positive and negative here by this red. So that's showing you sort of the pattern on the sky. So I said this antenna was only sensitive to one polarization. If the electric field was orthogonal to how it is, so if it went up and down, the electrons in these wires wouldn't move. So you'd need a dipole in the other direction, 90 degrees from this one, to be able to measure the other polarization of light. So that radiation pattern, as I said, it's a torus. So if you look over here on the left, that's what it looks like. But this is for a dipole that's vertical. So previously we were just imaging our dipoles horizontally. Here we have a vertical dipole, so you can see it a bit easier here. So here are the two halves of our dipole oriented vertically, and the sort of torus of the electric field around it. So, you know, this shows the torus a bit better, but here you can see the vertical dipole inside that torus. So for our case, with the horizontal dipole we were looking at, this torus would be rotated 90 degrees. So one thing we can do to increase the area, the effective area of our dipole, is to use something like a Yagi antenna, which you see over here. These are commonly used on houses to receive television signals. So you have parasitic antenna elements which direct the wave towards the dipole. Another common type of dipole antenna is the log periodic, which we will talk about later. Now, using a Yagi can give you more effective area to your dipole, but what if you want more signal, more gain? In that case, you can have an array of dipoles. So here you have, each of these is a dipole, so you have half of the dipole here, half of the dipole here, and then you just have an array of those. And those are actually quite useful. Pulsars were actually discovered back in 1968 using a dipole array. So the famous Jocelyn Bell, helped to build this very large dipole array. You can see her here working in the beautiful, wet English weather, setting up this dipole array. So this was a very large array. Over 1,000 of these wooden posts, 192 kilometers of wire, all hand cabled. Took 2 years to build. But it was effective. So going back to the Yagi antenna, here you see we have what look to be, on this diagram of a Yagi, 4 dipoles. But actually there's only one dipole, this driven element. This is the only dipole element that's actually attached to anything. So you can see the two halves are attached to this wire. All of the other elements are just passive. They're not attached to anything. So these two shorter elements, they are shorter than the driven dipole, that's important. They're director elements. They actually direct electromagnetic radiation towards the dipole to be received. Then in the back here you have another element. This needs to be longer than your driven dipole, and this acts to reflect any electromagnetic radiation that gets past the dipole back onto it. So what this does is this makes the Yagi antenna very directional. So if we look at a radiation pattern of the Yagi in both the vertical and the horizontal direction, we can see this main lobe, principal lobe. So this is more or less the beam of the Yagi antenna, you can think of it as. So this is where the antenna is most sensitive. So these diagrams are done with relation to the main beam. So the main beam has the maximum amount of power. And then you have what are known as side lobes. So the antenna is very sensitive in front of it, but it also is slightly sensitive at points off to the side. A little bit behind it, but not much. So these areas of increased sensitivity off to the side are called side lobes. Okay, so some basic definitions we need to know to talk about antennas. There's obviously a range of frequencies that antennas are sensitive over. So that range of frequencies denote the bandwidth of the antenna, which we call B. So the definition of B is F2 minus F1. So F2 is just the top of your operating frequency, and F1 is the bottom. So if you subtract it, say the top of your operating frequency is 800 megahertz, the bottom of your operating frequency is 400 megahertz, your bandwidth is in 800 megahertz minus 400 megahertz, so your bandwidth is 400 megahertz. So now Yagis and dipoles generally have a small fractional bandwidth. So the fractional bandwidth is the total bandwidth over the center frequency. So in the example I gave, you have 800 megahertz over 400 megahertz. So the center frequency there is 600 megahertz. So the bandwidth is 400 megahertz over 600 megahertz. So your fractional bandwidth is 2/3. Now, Yagis generally have even less than that in fractional bandwidth. But if we want more fractional bandwidth, more bandwidth in general, what we can do is we can use a log periodic antenna. So this is similar to the Yagi, but there are a few distinct differences. So one of the first differences to notice is that with the Yagi, we had one driven element and then several parasitic elements to reflect and direct electromagnetic radiation. With the log periodic, if you look at the dipole elements along it, you'll notice that they're connected. So this means that every single element in the log periodic is driven. Also, the sizes of the dipoles in the Yagi went from smaller to larger. The director dipoles need to be smaller than the driven dipole, and the reflector dipole needs to be bigger than the driven dipole. And there's a little bit of tuning that can be done. However, with the log periodic, there's sort of a linear increase in the size of the dipoles, and also the spacing. If you notice, the spacing between the elements gets bigger. This is because the spacing is logarithmic. That's where it gets its name log periodic, because the elements are periodic in log spacing. So all of these things combined give you a very, very large bandwidth. So in the example I gave for the Yagi, I said it could observe between 400 and 800 megahertz, which would mean F2 over F1 would be 2. That's a bit of an exaggeration for a Yagi even, but for a log periodic, F2 over F1 can be as much as 20. For a log periodic, we'd be looking at maybe 1 or 2. So for a log periodic, your F2 over F1 can be a factor of 10 larger. So, okay, we should just use these, right? Well, the problem with the design here is that the beam, the power pattern, the radiation pattern is not very nice. You can see it's not very symmetrical. The main lobe is very large, and also the side lobes are very large. So what this means is something, say, over here at 30 degrees would be received quite well by a log periodic. But if you're pointing at something, you probably want to see what you're pointing at and not something 30 degrees away. So in that case, you wouldn't want to use a log periodic. And also side lobes, which we'll get into more in depth later, they're quite big, which means you're quite also relatively sensitive to something 90 degrees away from where you're pointing. Okay, so let's talk about antenna gain. So what we need to do now is we need to define a theoretical concept of a perfect ideal isotropic antenna. So that is an antenna that radiates or receives. Remember reciprocity here. It doesn't matter if it's radiating or receiving. Its performance, its parameters are identical. An isotropic antenna is one that radiates or receives equally in all directions. Now remember, even our simple dipole only radiated or received in a torus. So that's not even a good estimate of this theoretical ideal isotropic antenna. Okay, so if we have this perfect theoretical isotropic antenna, then we can define our gain, our antenna gain, as the ratio of the power received by our antenna from some transmitter to the power received by the theoretical ideal antenna from the same transmitter. Now that ratio we define in units of decibels. So a decibel is a decibel, so 1/10 of a bell, just like a decimeter is 1/10 of a meter. A decibel is 1/10 of a bell. Bell was named after Alexander Graham Bell, who invented the unit. So it's a logarithmic unit, the bell. So the gain ratio is defined in decibels as 10 times the log of the two powers. So log of the ratio of the two powers. So here you have P2, the numerator, is the power received by our antenna, and P1 is the power received by the ideal antenna. So this ratio is going to be less than 1 always, because you're always receiving less power than theoretically possible. So just a small aside, talking about power ratios. So for, say, gain, if you're amplifying a signal, the gain in decibels we can define as 10 times the log of the power out over the power in. So if we're doubling the power, P out would be twice P in, so you'd have the log of 2. The log, this is base 10 log here, not natural log, base 10 log. The log of 2 is 0.3, 10 times that is 3. So if you were doubling the power, your gain would then be 3 dB. Power gain in terms of voltage, I very rarely see this used, so I'll just gloss over this. Loss is very similar to gain, it's just you've reversed the ratio. So if we have less power out than we put in because we're transmitting a signal over a cable, then you can measure the loss in dB that way. Now there's also these two useful formula for dealing with absolute powers if we don't have a ratio. So if we're, say, measuring the power into our receiver from space, we don't really have two powers. We're just measuring a power. But decibels are based on a ratio, so we need to relate our power to something. So in that case, we can relate it either to a watt, but actually in radio astronomy signals are very weak, so we generally relate them to milliwatts. So in that case, if you want an absolute power, you get a power not in dB, but in dBm. The m, the little m here, is for milliwatt. So if you have a power of 1 milliwatt, then you have a signal that's 0 dBm. So previously we've seen these radiation patterns. These are from a Yagi again, so you can see the very directed main lobe with the very small side lobes. So this main lobe we tend to call the main beam of the antenna. So one of the things we define with the main beam is the point at which the power, either received or transmitted, depending on what we're using the antenna for, but it doesn't matter because of reciprocity. We define the point at which the power falls to half of the value from the center of the beam, and that's the half power beam width. So it's the beam width at the point at which the power halves. So now that we know about decibels, if you look on these, I know they're probably a bit small, but this outer ring is defined as 0 dBs, so this is just normalized to the peak of the power of the main beam. So then I said a factor of 2 in power gives you 3 dBs, so there's a blue circle here that's fairly close to the outer circle, that's 0 dBs. This is the 3 dB point, so this is the point, this blue circle, at which the power has dropped to half. So if you find the point where your main beam crosses that 3 dB point and then look at the angle, that gives you the half power beam width. So here it's something around the order of 15 degrees here and 15 degrees here, in which case the half power beam width is about 30 degrees for this Yagi. And then of course you have the 3 dB point, but you also have in here the 10 dB point, the 20 dB point, the 30 dB point, and right in the center the 40 dB point. So one of the things to notice that I'll point out now, again in more detail, are these side lobes. And in between these side lobes you have nulls. So here you have the main beam, of course, and the first side lobe. Now, just between the main beam and the first side lobe, you can see that the signal drops to negative 30 dB. So that's that 30 dB point right there. So that's the first null. Then you have the first side lobe where the telescope's more sensitive. Then you have the second null, then the second side lobe, then the third null, then the third side lobe. So in the nulls, you're very insensitive, but then you're slightly more sensitive in these side lobes. As I said before, the most common antenna we use in radio astronomy is the parabolic reflector. The main reason for that is because it's frequency independent, so we don't have to worry about frequency constraints. The only problem is we generally need separate receivers for each frequency band we want to look at. So let's look at the physical parameters of a parabolic reflector. So in general, what we have is we have some diameter across the dish itself, plus a focal length. So the ratio of the focal length to the diameter is the focal ratio, and generally that's a measure of the depth of the dish. So if you had a very long focal length, in general it would mean that your parabola is very shallow. If your dish gets very deep, then near the edges of the dish, if you think of continuing this dish, the edges would become almost vertical, in which case the light they would focus would be very close to the top of the dish, in which case f would be very short. So then that small focal ratio would mean that your dish is very deep. So one important thing, and the reason we specifically have a parabolic dish versus some other spherical-ish shape, is that any ray that we emit from the focus, so if we take the focus of this parabola and we emit rays in different directions, they all will reflect off the parabola parallel to each other. So that's important because if we have a signal coming from space, by the time, say, a wavefront reaches us, it'll be parallel to the dish. And then any point along that wavefront, no matter where it bounces off the dish, will reach the focus at the same time. That's because the path length traveled by any of these three rays is the same. Even though, say, for Q3, its distance to the dish is shorter than for Q1. Q1's distance to the focus is shorter than Q3. So the total path length is the same. So all points along this line bouncing off the dish will arrive at the focus at the same time. So we can retain all of the phase information from this wave using a parabola. Okay, so we have, our parabolic main dish focusing light, but now we need to collect that light. So this is done with a feed antenna, or just a feed. So that feed needs to illuminate the surface. It needs to be able to see the surface of that dish so that it can pick up that radiation. If it's not illuminating the dish fully, we end up with spillover. That is light that we're losing because it's bouncing off of our main parabolic reflector and it's missing the feed, or it's hitting a bit of the feed because the feed isn't viewing the whole dish. Now, if we put a feed right at the focus, that's known as a prime focus feed. And generally, we use a horn feed for that. So we'll get horn feeds at the end of this lecture. Now, radio wavelengths are generally long, right? I mean, we're talking on the order of centimeters, much longer than even, visible light. So instead of the light being focused to a very small point, it ends up being focused to a small circle. So you can see that here. Now this is known as an airy disk. So actually you can see also some artifacts, some rings around that airy disk. So what we want to do is we want to tune our feed to sort of perfectly intercept that airy disk so that we get all of the power that's included in it without getting any of these artifacts around it. Okay, so how do we, why don't we just tune our feed to see right up to the edge of the dish? And why do we have to worry about any lost power not making it into our feed? Well, again, there's spillover, like I mentioned, that's light from the edge of the dish sort of missing the feed. But also, if you look at the structure of these telescopes, you have your feed, but it's in front of the telescope. So light that hits the back of your feed just bounces off. It never hits the dish. So there's sort of the shadow of the feed on the dish. There's also support structures holding the feed up above the dish. They're going to block light as well. And of course, while the dish is smooth, there are surface errors that cause phase problems. We'll get into that in depth later. So let's look at the power pattern of a beam. So this beam pattern is for a 25-meter dish, which is a typical size for a radio dish, observing at frequency of 1 gigahertz, which is a typical observing frequency for radio astronomy. So here you can see the main beam, followed by the first null on either side, and then the first side lobe. So you could say the total width of the main beam is about 100 arc minutes, because this first null is about 50 arc minutes from the center of the beam. So the total width of the beam is about 100 arc minutes. But again, we tend not to talk about the total width of the beam. We want to know the full width at half power, right? So here's the half power point, 50% of the total power. So there we're looking at more like 25 arc minutes on either side of the beam. So a full width half power point of about 50 arc minutes in total. So we'd say our main beam there is about 50 arc minutes wide to the half power point. Okay, so there are a couple different types of designs for mounts for radio telescopes. Now, most modern radio telescopes have what's known as an alt-az mount. So that's altitude and azimuth. Altitude can also be called elevation. So those rotate around two axes. You can see one over here. So you have sort of a structure that rotates around in a circle down here, and then your telescope can tip up and down around this axis. There's also the polar mount, so that's this design here, and that just has one axis here, and the telescope rotates around that one axis. So here you have to place this mount so that this axis is pointing at the celestial pole. So one disadvantage to the polar mount is that you can only track a source for 12 hours, whereas with the alt-az mount, you can track a source for as long as it's above the horizon. Another disadvantage with the polar mount is you have to use heavy counterweights back behind the telescope. But there are disadvantages to the alt-az telescope. So the main disadvantage there is that your beam rotates on the sky. And if you're doing something like a polarization measurement, you need to correct for that. So that's shown here. We'll just go to the next slide so we can get a closer picture. So if you have some source, so that's this little lobed structure here, that's going to be rotating around the celestial pole as the Earth rotates. Now, this ellipse here is our beam on the sky for an Altaz telescope. Now, with the Altaz telescope, since the telescope dish itself never rotates, it just spins around in a circle and points up and down, you can see that the beam never rotates on the sky, but of course the source does. So the source rotates inside the beam. So again, this is what you need to correct for. With the polar mount, since the dish rotates with respect to the Earth, the beam stays fixed on the sky, so your source will never rotate in your beam with a polar telescope. Now, even with the disadvantages of the polar telescope, there are, examples. There's the Westerbork array in the Netherlands. So here you can see the large counterweight that I talked about. That's one of the disadvantages of the polar telescope. This is just a lot of concrete, so it's quite heavy and quite hard to deal with if you need to maintain it. Okay, so we've talked about the simple configuration where we have our main reflector and then a feed antenna at the prime focus. But there are other configurations we could use as well. We could have an off-axis feed where we have the support and the feed sort of bolted onto the side of our main reflector instead of over the center of it. And in that case, there's no blockage. But also, we don't have to have the feed at the focus. We can have a subreflector that re-reflects the light, so the light reflects off the main reflector, re-reflects off the subreflector, and is then captured by our feed. So there's two main types of those. There's the Cassegrain, where we have a convex hyperbolic secondary, and the Gregorian, where we have a concave elliptical secondary. So these are the Cassegrain and the Gregorian are very similar systems. The main difference between them is with the Gregorian system, the focus is in front of the subreflector, whereas with the Cassegrain, the focus is behind the subreflector. So you actually still have access to the focus in a Gregorian system, which is quite useful if you want to put a feed temporarily in front of, a prime focus feed temporarily in front of the subreflector. You can do that with a Gregorian, you can't do that with a Cassegrain system. So here's just some sort of ray traces of the different types of reflectors we just went through. So prime focus, your light comes in, hits the main reflector, is directed directly into the receiver. With a Cassegrain, you have, of course, your hyperbolic convex secondary. Light comes in, reflects off your main surface, re-reflects off the secondary, and is received. There's also an offset Cassegrain, which will come up a bit later. The idea there is you have the same Cassegrain subreflector, but instead of receiving light directly underneath it, your receiver is offset from the center, so there's a bit of an asymmetry there. There's also a Naismith setup, so a Cassegrain subreflector, but instead of receiving the light immediately, you reflect it once. A beam waveguide, which similar, you have a subreflector, and then you bounce your light, or you direct your light down a waveguide into your receiver. And finally, the dual offset. Again, you have a completely unblocked aperture where you're not losing any light to the where it's bouncing off either the back of the feed or the support legs, as you have in all the other designs. So here are some real examples. So for prime focus, you have the GMRT in India, so the receiver's up there directly at the focus. For a Cassegrain, here is MOPRA. Offset Cassegrain, we'll look at this a bit later as well. There's the VLA. We have a nice close-up of that, and you'll understand why we need to do the offset Cassegrain. For an example of a Naismith telescope, OVRO, beam waveguide NRO, and dual offset Gregorian. This is very popular nowadays. SKA, Meerkat, GBT, Allen telescope array. So of course with the offset antennas, like all these I just talked about here, you have no blockage and you have a cleaner beam. By cleaner we mean given the blockage from the feed and the supports in other telescopes, for example, Cassegrain and prime focus, they give you artifacts in your beam that you have to deal with in imaging, that you don't have those artifacts with offsets. So, okay, the nice thing about using a prime focus is you can use it across a full frequency range. But then your receiver is at the prime focus. So if we look at the GBT, for instance, this is a very large structure. Of course, this is the largest fully steerable telescope on the planet. It's a Gregorian system, so here's the Gregorian secondary up here. But of course, that's very close to where the prime focus is. That's several hundred feet in the air. So getting up there is difficult. So that's a disadvantage of a prime focus. With a Cassegrain system, of course, if you remember, we have a subreflector, and then the receivers look to be below the dish. So the receivers are lower to the ground, so they're easier to get to. You generally don't have to climb the entire structure. The problem there is low-frequency receivers become very large. So in general, even with a Cassegrain telescope, a low-frequency receiver will be at the prime focus. So actually, that is the case for the GBT. The GBT is a Gregorian, but it has a low-frequency receiver that operates at about 350 megahertz that swings up in front of the Gregorian secondary into the prime focus. And that's why the GBT has a Gregorian secondary as opposed to a Cassegrain, because the Cassegrain would limit access to the focus, and then they wouldn't be able to put that 350 megahertz receiver at prime focus. So back to Cassegrains, off-axis Cassegrains. The reason for the off-axis nature, so for the VLA antennas, this enables frequency flexibility. So that means they can change the receiver very easily. So they have the receivers located on a plate, a circular plate that they rotate, and the center of that plate is in the center of where the focus would be. But of course, all the receivers are on the edges of that plate, so they offset the focus to the edge of the plate, and then they just rotate whichever receiver they want into the field of view of the secondary, the offset Cassegrain secondary. So that's good, but the problem is being asymmetrical, that introduces characteristics that you have to deal with later, artifacts, polarization artifacts that need to be dealt with later, so it's not a perfect solution. Okay, so back to Gregorians like the GBT. The GBT is an offset high Gregorian. So offset, there's no blockage of the aperture by the receiver or the secondary, and you can see that the secondary is above the dish. Now, there's also the idea of an offset low Gregorian. So that has all of the advantages of an offset Gregorian. Again, no blockage of the aperture by the secondary or the prime focus, but also the receivers are closer to the ground. So here's an example of that. So here are some Meerkat dishes. So again, you can see offset Gregorian. You have your main dish, and then there's your secondary there, not blocking the aperture at all. But now this is low to the ground. Instead of being on the top of the telescope, it's on the bottom of the telescope. So with the GBT, if you point that to the ground, if you point it to the horizon, so it's as low to the ground as it can get, the receivers are still very high in the air. Here, if you point this telescope at the ground, the receivers would be quite low to the ground, much easier to access and maintain. So now, as I've been saying, we're going to take a look at this off-axis Cassegrain on the VLA. So here's sort of a view of the receiver room. So you can see there's this circular plate, there's all these receivers, these holes are, each of these is a receiver. And so the central axis of this plate is this spindle right here. So this is the central focus of an on-axis Cassegrain Gregorian system. However, because these receivers are off to the side, you can see them sticking up above the plate here. Here's the main reflecting surface. The light that bounces off of the secondary can't come straight down. It'll miss the receiver. It needs to bounce off to the side. So that's the use for an offset Cassegrain or an offset Gregorian system, is to allow you to just change this. Instead of having to have someone go in, unbolt a receiver and bolt a new one in place, you can just hit a button on a keyboard and this table will just rotate around and put whatever receiver you want into the path of the light. There are some other approaches to dishes. There's one mildly odd-looking dish we have at Jodrell Bank where I work. It's called the Mark II. So this was an experimental telescope. So you can see this is sort of an elliptical aperture. So the idea was they were trying to design larger and larger telescopes. And if they wanted to build a 300 meter, they thought instead of building it 300 meters off the ground, which would be very expensive and difficult to do, if they instead got the same collecting area by making the telescope narrower in the vertical direction but wider, they could get it closer to the ground. It turns out this is not a great idea. The elliptical aperture gives you a very complex beam shape on the sky, which is very hard to deal with. So you can actually see there's the elliptical aperture, but then on top of that you can see what looks to be a newer surface. So we're going to talk about surface accuracy, but there was a newer surface put on that has a better accuracy than the original one, but also that's actually a round aperture. So these bits, these wings on the telescope aren't used, because this telescope is still in use. It's being used as we speak, actually. But the used part of the telescope is no longer these edges. There's also cylindrical telescopes. So these are sort of sections of a cylinder with receivers arrayed along the length of that section. So there was one that was built in India in Uti, you can see here. So these are much cheaper to build than a normal parabolic dish. There's a lot less metal here, of course, but the problem here is you have a non-symmetrical beam pattern, so it's a bit more difficult to deal with. Some other sort of novel examples, there's the Rattan 600 in Russia. So here you have, if you can see this sort of white circle around this field, this is pretty much the rim of, you can think of this as the rim of a parabolic dish. So what this does is it focuses light towards the center of the field. So here's a close-up of the center of the field. So you can see in the background, there's that white sort of rim running around. So the light is focused in. It hits this inverted cone and is reflected down underground where all the receivers are. It's a very, very interesting design. Not sure how well it works. Similar design on the Nancy telescope in Nancy, France. Here you have a flat reflecting surface that can be aimed in elevation to point to a strip on the sky. So light will come in and reflect off that towards this curved screen here. And this curved screen here will focus light towards the center of this field. And the resolution of this image isn't great, but right at the center of this field is a building that has the receivers in it. Yet another design is this idea of a cross antenna. First cross was built by this guy Bernie Mills in Australia. So if you take a strip of a parabola in one direction, what you have is you have a beam that's very wide in the direction in which the antenna is narrow, but in the direction in which the antenna is wide, the beam is very narrow. So if you then take another strip of a paraboloid and cross it with your first strip, you have a beam at the center of those which is narrow in both directions. And the problem with this design is that you get very high side lobes. Remember, we don't want side lobes because we don't want sensitivity where we're not pointing. So here's a picture of that first cross antenna built by Bernie Mills in Australia. And there are some other crosses as well. That wasn't the only one. There's the Melanglo cross, also in Australia, and the Northern Cross in Italy. But it's not just old telescopes that use this sort of cylindrical design, as we saw from the UDI telescope. There's also Chime, which is a fairly new telescope. So this is the Canadian H1 Intensity Mapping Experiment. H1 is neutral hydrogen, if you don't know that. So Chime, what it is, it's some sections of cylinders, four sections of cylinders lined up with receivers above them. The little green blobs are the receivers. So these have a fan beam on the sky. Like I said when I talked about the UDI telescope, the beams aren't symmetrical. So you end up, each of these little receiver elements gives you a point in this fan beam. And as long as the beam shape doesn't bother you, as if you were mapping, say, for mapping neutral hydrogen, as this telescope was built to do, it's a good design. Of course, we have also single fixed large dishes. We used to have Arecibo until its recent collapse, which was 300 meters, but we also have FAST now, which is 500 meters. So these are pretty impressive sizes, but there are some caveats. So both of these telescopes aren't actually parabolic. Both of them are spherical. So, of course, for a parabola, if we imagine, say, Arecibo, this is a cartoon of the Gregorian dome. That was at Arecibo. A parabola focuses light to a point at its focus, which is great, but that's for a plane wave incident on that parabola. Remember, as a plane wave comes in, all of the points along that plane wave, regardless of where they hit on the parabola, arrive at the focus at the same time. But that's not true if the wave isn't incident on the parabola directly. But of course, if we're using a pointed parabolic antenna, we're pointed at what we want to look at. But if our dish is fixed, we can't really point it. So we need something that responds well in all directions. So it turns out that is a spherical surface. So pretty much from any direction it works equally well, but it doesn't focus perfectly. And the main reason there is because a spherical reflector will focus waves into a line instead of a point. Okay, so that's a problem. But if we look at a spherical reflector overlaid on a parabolic reflector, near the vertex of both, they're a fair approximation for each other. It's only really an issue when you get to the edges that you get a very large deviation. Now the thing is, the interesting thing here is, while Arecibo was 300 meters and FAST is 500 meters, that entire surface isn't used all at once. So you're not illuminating the entire 500 meter spherical surface of FAST at any given time. And that's shown fairly well here. So here is the surface of FAST. This is a little bit of holography done to show deviations from a sphere, from a spherical surface. The surface of FAST is active, and what that means is there are a number of panels on this surface, but they don't just sit there. There are actuators underneath the surface at the corners of the panels that can move them up and down. So what you're seeing here in this holographic image here is the 500 meter aperture, but a smaller portion that's being pulled into a parabolic shape. So for Arecibo, what they used to do before it collapsed was it was a passive surface that was spherical. So in order to correct for that, they had a secondary reflector in the Gregorian dome that was a very, very, very funny shape in order to take that light that wanted to be focused into a line and focus it into a point. Then they also had a tertiary reflector. They had a third reflector before the light actually reached the feed. So FAST gets around that by having an active surface and pulling the part of the dish they want to use into a parabola. Then they can just receive the light directly in a point, because this little bit of parabola will focus light incident on it into a point. So of course, in this configuration here, FAST is observing something that's over here in the sky coming in. As I said, of course, with the spherical dishes of FAST and Arecibo, you have a limited range of what you can do. You don't really want to get near the edges. The spherical reflectors are only best approximate a paraboloid near the center. Of course, FAST can deal with this, but Arecibo couldn't. But the way to point is by moving your secondary. Now, you're physically moving this above the telescope, so there's a limited range. So Arecibo was restricted from -1 degree to 35 degrees in declination. FAST can cover more than that. FAST can go from -14 to 66 degrees in declination. Less at full gain, so it has reduced sensitivity, of course, as it gets near the edges of the sphere. But with full sensitivity, it can still go from -1 degree declination to 52 degrees declination, which is still better than what Arecibo could do. So FAST can track a source for about 2 to 3 hours. I mean, compared to a polar mount telescope, which can track a source for 12 hours, or compared to a Altaz telescope, which can track a source for, as long as the source is in the sky, that's a lot lower, but you can't have, a 500 meter aperture that's fully steerable. Okay, there are some further limitations on dishes. So the main limitation is the diameter of your dish as measured in wavelengths. So the diameter divided by the wavelength of light you're looking at has to be greater than 15. I mean, that's not a huge deal, because in general, if we're looking at, say, 1.3 centimeter to 13 centimeter wavelength light, pretty common for radio. For a standard 26 meter dish, d over lambda is anywhere from 200 to 2000. So we're well above the 15 we need to be. Also, the second limitation is deviation from a true paraboloid. So this pretty much comes down to surface accuracy. So here's a holographic measurement here. You can see the areas that are green are where the surface matches a theoretical paraboloid, but other areas it's deviating from a paraboloid. So these are errors in the surface, and those errors affect your pointing and how good your images look. So if we use this formula here called the Ruse Formula, named after someone, that can tell us the surface efficiency. So the efficiency eta of the surface is just equal to e to the negative 4 pi sigma over lambda squared. So here lambda is our observing wavelength, and sigma is the RMS error in the surface. So if we rearrange that equation, so take the natural log of both sides, we get this expression for the RMS error in the surface over our observing wavelength is just equal to this. So if we take the minimum typical surface efficiency of 70%, plug that in here, we can get that the required surface RMS accuracy is about lambda over 20. Then if we, say, observe at 43 gigahertz, where the wavelength of that light is 7 millimeters, the surface accuracy needs to be around 350 microns. So that's about twice the width of a human hair. So if we want to observe at 7 millimeters, our surface has to be perfectly smooth down to about the width of a human hair, which is very, very, very smooth. I mean, you can just, make metal panels and polish them really well and lay them out nice and maybe do a holographic measurement to make sure they're all smooth, but there are changing forces that are acting on your antenna that sort of fight against you having a smooth surface, like wind pushing on the dish and deforming it, solar flux that's going to heat up the dish, and of course metal expands, and the top edge of the dish will expand over the bottom edge of the dish, which is probably in shadow. There's gravity deforming the dish depending on which way the dish is tipping, so it's kind of hard to keep your surface as accurate as you build it, as you're pointing the telescope. So talking about general antenna performance then, we have what's known as aperture efficiency. So again, eta here for efficiency. So we're defining that as the power collected by our feed over the power incident on the antenna. So what we're saying is we're not able to collect all of the power. That's always less than 1. We're not able to collect all of the power falling on our antenna. And so our efficiency, our aperture efficiency, is actually the product of a bunch of other efficiency terms. So there's, again, the surface efficiency, which we talked about in the previous slide. There's the blockage efficiency, right? This is blockage due to, say here, the feed being in your way or feed supports getting in the way of light. Again, this term goes away if you use an offset Gregorian where you have no blockage. You also have feed spillover, right? So that's where light hitting the edge of your main reflecting surface is bouncing past the feed instead of into the feed. Feed illumination efficiency. So in that case, that's how much of the dish your feed can see. If you look too close to the edge of the dish, you might end up seeing the ground, and the ground is hot. 300 Kelvin, so you'll end up getting a lot of extra radiation you don't want from that, increasing your system noise, which is bad. So you want to taper your feed illumination in a little bit, but also the illumination isn't always round. You can see here is a measurement of the feed illumination of a dish, and it's kind of square. So actually, these little bits of the dish in blue aren't being seen by the feed. So your feed illumination isn't perfectly efficient either. And then there are other miscellaneous losses as well. So in general, aperture efficiency is only about 65%. It seems low, but it's, given the number of things that go into it, that's a pretty good number. Okay, so how big can we reasonably build parabolic radio telescopes? I mean, we've seen that we can build large ones in the ground that don't move, but if we want to point one, how big can we reasonably go? Okay, as we increase the diameter of a telescope, the problem is it gets heavier. So the load from gravity is bigger, and you need to compensate for that by building a stronger structure underneath it. Of course, that adds weight and costs money. But then if you have a very large dish, you probably want that dish to be smooth for surface accuracy. You can make a mesh dish. For example, the GMRT is a mesh dish, but the surface accuracy of that is low. It's fine for, say, 1 gigahertz observations, but if we want to observe at 43 gigahertz, remember we need 350 micron surface accuracy. So you have to make your dish very smooth. But if you make your dish very smooth and very big, it acts like a huge wind sail. So if you were to point a huge dish into the wind, the telescope would want to blow away. So you need the structure to be able to support the telescope from being moved by the wind. It turns out the wind distortion on a parabola goes as the cube of the diameter. and also the cost of building an antenna goes as the cube of a diameter. So in general, what we'll probably see is right now the largest fully steerable telescopes on the planet are, on order 100 meters, and anything bigger is a stationary spherical reflector in the ground, and that's largely what we'll see going forward. So there was a proposed telescope at Jodrell Bank, the Mark V here, which was going to be 305 meters, about the size of Arecibo, but fully steerable. So this was actually designed back in 1970. You can see the design here. It's just the cost was unfeasible. You can see there's a lot of metal here. Okay, so we know about aperture efficiency and total efficiency and pointing efficiency, or surface accuracy, but what about pointing errors? We'd like to point at what we think we're pointing at, but that's not always the case. There's often some pointing error. So that pointing error, we want to be below 1/20th of the full width half max of the main beam. So this theta 3 dB is just the full width half max of the main beam. So we want our pointing error, delta theta, to be less than 1/20th of that. So if, for some reason, gravity or wind, your antenna is pointing 1/20th of a full width half max away from where you think you're pointing, if you're pointing at some bright source, you will lose less than 1% of the intensity from that source. If you're only pointing away from that source by that much, the full width half max over 20. If you somehow the beam moves an entire full width half max, so that means that the source you want to point at is at the full width half max point of your beam, so the edge of your beam, considering the full width half max being what we consider the edge of the beam, then you'll see a 10% loss in intensity from that source. And if you think you're pointing at the source, and then you quote the intensity of that source as that number, you're going to be 10% wrong. Also, if you're imaging, that can lead to very bad results. So when you go to higher frequencies, the beam gets smaller. So you need to be, your sort of pointing error, if your full width half max gets smaller, your pointing error gets much smaller. Your pointing error limit gets much smaller. So often at higher frequencies, in the tens of gigahertz, what'll happen is when you go to observe, you'll do a quick check where you scan over a source in one direction and then another direction on the sky, either in a plus or like an X, to see where the source peaks, to see if you think you're pointing where you're actually pointing. And again, at higher frequencies, your beam gets smaller, but also with larger antennas, your beam gets smaller. So pointing becomes difficult with those two constraints. Okay, so that's all related to the dish itself, but we need to move the telescope. So there's performance we need to think about when we're moving the telescope based on the servo motors. Now we want the telescope to move fast because we want to be efficient in our observing. If we're observing multiple sources, we want to spend our observing time observing the sources, not slewing between them. And also, if you're doing observations where you need to calibrate and you're switching between, say, some target source and a reference source every few minutes, you want to spend as much time on those sources as possible and the least amount of time slewing between them. So typically, for a modern dish, you can go about 90 degrees per minute in azimuth. That's sort of the around direction again. And 30 degrees per minute in elevation, so tipping the dish up and down. Now again, these dishes are big. Most of the common size of dish is 25, 26 meters. The Meerkat dishes are smaller, 13, 14 meters. But they're still big pieces of metal. There's a lot of momentum behind them. So when you stop them, when you get on source, they still take about 2 seconds to settle down. And also when you want to move the telescope, it takes about 2 seconds to accelerate the telescope up to full speed, just because it's a lot of weight to get moving. So you want the structure to be rigid. Of course, if the telescope is very wobbly and you stop moving it, it's going to wobble around for a while before it settles in. If it's very rigid, it'll settle in very quickly, so you can get on source faster. If it's wobbling, you don't want to start observing until it's finished wobbling. Otherwise, your source is going to be drifting around in your beam, so you're not going to be you're not going to be observing the intensity you think while it's wobbling. Also, if, say, the support structure for your subreflector or feed is not rigid, and you point down at the horizon, say this structure would sag in one direction, then you point up at the zenith, straight up, this structure here, this support structure compresses, and your feed gets closer to the main dish, your feed or your subreflector, which means it moves out of where the focus is. This structure was built to keep the feed or subreflector in the focus, and if this sags, then this point moves out of focus, in which case you're measuring, you're going to lose sensitivity, and if you're imaging, your image is going to be blurry. Okay, so let's define some quantities based on antenna performance. So the first one we have is flux density, which we call S. So the flux density S is just equal to the Planck function, which is I. That's a function of our frequency nu. So it's the Planck function integrated over the solid angle. So the units on that are watts per meter squared per hertz, which is a unit that's close to, those are the physical units of what's called a Jansky. Now, the Planck function, I of nu, it's a fairly complex function if you look up Planck's law. So it's slightly difficult integral to do. However, at radio frequencies, although we can observe at high radio frequencies in the tens of gigahertz, pretty much the whole radio regime is fairly low frequency. So there's a low frequency approximation to Planck's law called the Rayleigh-Jeans law. And as long as we're in the Rayleigh-Jeans regime, as long as the frequency we're at is in the Rayleigh-Jeans regime, we can use the Rayleigh-Jeans law to replace the Planck function with this function right here. That is 2k, the Boltzmann's constant, t sub b, nu squared over c squared. Now, Tb is the brightness temperature of the source. So of course 2, Boltzmann's constant, nu, and c are constants, so we can pull them out of the integral. So by using the Rayleigh-Jeans approximation, now our flux density is just some constant times the brightness temperature integrated over the size of the source. Further, if our brightness temperature is uniform across the source, that becomes a constant and it can be pulled outside of the integral. So then you just have a constant times the integral over the source size. So you just integrate over the source size to get the source size, and we have what's known as integrated flux density. So then you would just have this constant times the source size. And this is if your beam size matches the size of the source on the sky. Because there could be, if your beam size is bigger than the source on the sky, there could be flux from outside the source in your beam. And if your beam size is smaller than the source size on the sky, you're not collecting all of the flux from the source. So another parameter that's often quoted in papers is the peak flux density. So that's normally quoted in Janskys per beam. Again, Janskys are related to watts per meter squared per hertz. the definition is actually 10 to the negative 26th watts per meter squared per hertz. That's 1 Jansky. Okay, so we know that if we have a parabolic antenna with an aperture size of d, a diameter of d, and we're observing at a wavelength lambda, we have some beam that's cone-shaped because it's diffraction limited. So it's a cone, it has some solid angle. So to calculate that, we're going to assume that angle is small. It is. Remember, small angle approximation works if your angle's less than about 10 degrees. So in that case, the solid angle of our beam is pi over 4 times theta squared. So we know theta is just lambda over d, so we can approximate our solid angle of our beam as lambda squared over d squared. So let's go back quickly. Oh, can't go back. I'm recording. Sorry. So on the previous slide, we had our integrated flux density, which had an omega A beam size on it. So if we plug that in, we see we have flux density is 2k, Boltzmann's constant, t over lambda squared. And then omega A here is lambda squared over d squared. So lambdas cancel out. So we just get that our flux density is 2kt over d squared. So here our flux density now no longer has a wavelength dependence, which is good. So now I'm going to tell you from out of nowhere that the power into a receiver is given by this equation here. So the power into a receiver P is related to the aperture efficiency, eta, the area, d nu, and related to the flux density. So if we equate these two now, because they both equal flux density, we can see that the power into the receiver is just kt d nu, some small frequency. So say bandwidth or say a channel width. Now here, the T is what we call antenna temperature. We usually denote it as T sub A. This is different than the brightness temperature. This is the temperature we're seeing that seemingly our antenna is increasing by when this astrophysical electromagnetic wave hits it. So if we have our roughly standard 25-meter telescope and we observe 100 millijansky source, remember we defined a Jansky as 10 to the negative 26 watts per meter squared per hertz. So we have a 100 millijansky, so that's millijansky 10 to the negative 29th watts per meter squared per hertz. Seems very, very, very small, and it is. 100 millijanskys is relatively bright for a radio source. That's why we need big dishes to observe them. So if we have a 25-meter dish observing a 100 millijansky radio source, the antenna temperature we measure is 0.023 Kelvin. So that source is seeming to heat up our antenna by 0.023 Kelvin. And that's the power we're measuring. Seems to equate to that much of a change in the temperature of our antenna. So earlier I mentioned I would get back to feed horns when I was talking about prime focus feeds. So what we need to do with the feed horn is we are using our main dish, our main reflector, to direct our radiation towards either a subreflector or the feed horn itself. Even if it hits the subreflector, it's going to re-reflect towards a feed horn. So this feed horn then, what it does is it needs to channel the electromagnetic radiation into our receiver. So it has this horn shape, which is why it's called a feed horn. So it funnels down. Again, the aperture of the feed horn, the opening, is made to match the size of the airy disk, if you remember from earlier. So that is the size of the focal disk, because we're at long wavelengths, so the focus isn't a point, it's a small circle. The opening of this feed horn then matches that small circle. But then you need to funnel all that radiation down into a smaller point to get it into your receiver, because you don't want to build your receiver to be enormous. You'd like to focus all that down to a reasonable size. So of course you want the feed horn to be round to match the area disc, but also because you want it to illuminate the surface of the dish as well as you can. So the dish is round, so you make your feed horn round. If you see these ridges inside this feed horn, so you can see them here in this diagram, those are to make sure that the electromagnetic waves coming down into the feed don't couple to the feed itself. They're just directed down the throat of the feed instead of, say, setting up a standing wave inside the feed. So if we have a feed, say a prime focus feed, here above a dish, we have some angle M that the feed can see. So if M is very narrow, in general, your feed gets larger in units of wavelength, right? So the opening angle of the feed, it roughly goes as the diameter of the telescope over the focal length. So it's the opposite of the focal ratio, which was f over d. This is d over f. We can define the feed aperture diameter, so the width of the feed. So that is just lambda over d times f. So it's pretty much f over d, our focal ratio, times lambda. So we can see, f and d are fixed for our telescope, of course, but lambda changes. So at larger wavelengths, the aperture of your feed gets larger. So if we look at the top of a receiver room, so this is the top of the Gregorian receiver room on the Green Bank telescope. So you can see the receivers arrayed around on this plate that spins around. So short wavelength receivers are very narrow, but this 21 centimeter neutral hydrogen H1 L band, we call it receiver, is very wide across for these reasons, in order to be able to illuminate that whole surface. So speaking about illumination, the feed is not illuminated uniformly. Now, by that I don't mean that the feed doesn't see out to the edges of the dish. What I mean is the entire field of view of the feed isn't uniformly illuminated. If it were, like we have here, the beam would look like this, the beam of the telescope. So your main beam would be relatively narrow, but you would have kind of high side lobes, which isn't good because we don't want to be sensitive to things we're not pointed at. If you instead illuminate the feed more towards the center and taper the illumination off towards the edges, as in these 4 examples here, you can see your side lobes decrease a lot. Now your main beam gets a little bigger, which decreases your resolution, but again, your side lobes decrease. Now if you over-illuminate, like here, if you illuminate the edges of your feed more, or at the extreme, illuminate just the edges of your feed, your side lobes get enormous. You get a very narrow beam, which is great for resolution, but your side lobes get enormous, and you really don't want that. So you generally want a centrally illuminated feed. Now, we know the light hits the surface. We understand how that parabolic surface works. It reflects to either the feed in a prime focus or a subreflector, but eventually gets to the feed. We've just learned that the feed horn then directs those waves down its throat, but now we need to get it into the receiver. We need to get that light into the receiver. So what we do is we use waveguides to do that. So these are metal guides that allow electromagnetic radiation to propagate down them, and they have to be tuned to the frequencies we want to propagate, because otherwise frequencies that these guides aren't tuned to will be heavily attenuated and might the electromagnetic wave might not even make it down the entire waveguide if the waveguide isn't tuned for the right frequency. So these are generally these waveguides are either rectangular or circular, and there's a number of different modes that they're tuned to allow to pass through them with minimal loss of signal, because of course you don't want to lose any of your signal transporting it around. So here are some physical waveguides. So what we have is these waveguides here in this upper picture. These are called orthogonal mode transducers. So here these bolt onto a circular feed horn, and then the waves will propagate down this transducer. And so what these waveguides do is they split the polarizations of light into two linear polarizations. So you can see there's a slit in the end of this that's horizontal, and on the side you can't see. On this OMT there's a vertical slit, and on this bigger OMT here you have a vertical slit, and then at the end you have a horizontal slit. So the light that comes in is then the horizontally polarized light, in this case, won't propagate through this vertical slit, but it will propagate through this horizontal slit. And the vertically polarized light that comes down will propagate through the vertical slit, but not the horizontal slit. So you split your light into two polarizations that way. Alternatively, the light coming in is most likely circularly polarized, and of course if it's circularly polarized with the OMT, you're splitting into two linear polarizations. But if you want to retain the circular polarization of light, you can use a hybrid polarizer, like in the bottom picture here. So in this case you have both right and left circularly polarized light coming in down this waveguide, and the right-handed circularly polarized light will propagate down one of these paths, and the left circularly polarized light will propagate down the other one. So you can split your circularly polarized light that way, while still retaining the original circular polarization.